Yeah, thanks for that kind introduction and thanks for inviting me. I'm really excited to be here because I was once a student at LIDS as well, like you, like over 10 years ago. I'm not going to say exactly how long. I was advised by Yuri Poliansky and Muriel Medard, so I had a foot at LIDS and a foot at RLE. And when I look back, those were like some of the best and most intellectually stimulating times in my research career. So I hope y'all enjoy it. And it's great to be back here to share some of the work that we've been doing down and now across the river at the School of Engineering and Applied Sciences at Harvard. So since this is a student conference, I thought I would take the first about 10 minutes of the talk just to say a little bit about what my research group does at Harvard, and particularly how we work both with information theory and also applications in machine learning AI, focusing on private, responsible design of these algorithms. And one of the reasons we use information theory is because information is everywhere in machine learning. When you think about the information in a machine learning algorithm, or now I guess an AI algorithm, usually what comes to mind is the data set, the data that you use to train this algorithm, and how information from the data is somehow mapped onto the weights of your model in order to do some kind of classification or prediction task. But the truth is, in the pipeline of designing these models, there are many other information sources. For example, there are design choices that are made by the people developing those algorithms, like the model class, the number of parameters, your regularization strength, your train test split, the choice of training algorithm and optimization, even the random seed that you choose to initialize your weights, right, determines which local minima you're eventually going to converge to, and ultimately how your model is going to perform and what kind of predictions it's going to make. And all that information is mapped to the model after training, and that could lead to unintended consequences when these models are deployed. One such consequence are privacy risks. Models can contain information about the training data, and just by examining these weights or the input and the output of the model, you might be able to reverse engineer potentially privacy-sensitive data used during training. Such privacy attacks have been widely documented in the literature. Models can also encode biases and have disparate performance on different population groups. Specifically, even though your model might be accurate on average, when you evaluate that model on different groups, you might see a disparity of performance. And these kinds of disparities have also been widely documented in applications that go from facial recognition to policing to education and so on. Generative models, right, they can produce outputs that also inaccurately represent population statistic. This is one example that we did in our group, where if you input the query a photo of a computer program for the ENIAC on Google image search, historically the main programmers of the ENIAC were all women, but if you add the same prompt to Stable Diffusion, you get a bunch of pictures, black and white pictures of men. And this could be a challenge not only from a kind of moral sense, but this is a challenge also when you're deploying these models in practice, because when you don't account for this, you can get headlines written about the models that you're deploying in your company, like Gemini's AI image results might offend your users. This is an incident that happened with Gemini's AI image generation algorithm about a year ago, where these algorithms would inaccurately represent certain populations. And in some cases, these models can have no information at all for certain inputs. The model output can be arbitrary, an artifact of the randomness used during training. This is another example that we did a few years back, where we trained a convolutional neural network to detect different spectrograms and detect what kind of sound is in that spectrogram. And simply by changing the random initialization of training, you keep everything the same, the data is the same, the model architecture is the same, and so on, but just changing the random seed that you use to initialize your training process, you end up with models that have different weights that on average have approximately the same performance, but on individual samples, they make conflicting predictions. And sure, in an application like audio recognition that might not seem like a big deal, that's known as the Rashomon effect. But when you look at other applications of social consequence, like content moderation and so on, decisions supported by machine learning models may depend on arbitrary and unjustified choices during their development. So what I'm going to do today is to talk a little bit about some of these challenges and how we use tools from information theory to address challenges in privacy, in fairness, and in arbitrariness. Information theory is a tool set of choice because information theory allows us to delineate the limits of these machine learning systems that are independent of specific models, applications, and semantics. We can really try to get at some of the heart of these problems. So, and in order to understand how we apply information theory in these cases, there are two questions that I'm going to answer. If you've already taken an information theory class here at MIT, this is going to be pretty obvious for you. So just sit back and relax. If not, you're going to learn something new. And we have to answer, how do we measure information and how do we model information? Right, so how can we measure information? How do we quantify it? So information in information theory is measured as a change in uncertainty. So if I tell you that the sun will rise tomorrow, that's a statement that's significantly less informative than when I tell you that the outcome of the dice roll of a row of two dice, the sum of the faces of two dice is 12. And the reason why the first statement is less informative than the second is because I'm pretty sure the sun will rise tomorrow, right, with probability overwhelmingly close to 1. But if you ask me what's my prior belief of the outcome of the sum of the row of two dice, I have much more uncertainty. And once I observe that dice roll, that distribution collapses to a single distribution here. So in general, information is measured and quantified in terms of these difference between beliefs as represented by probability distributions between the state of a system. And one way of quantifying this change in distributions is using something called a divergence measure. And there's a world of divergences to choose from. There's integral probability metrics, F divergences, Bregman divergences, and so on. Today in this talk, we're going to spend a lot of time talking about F divergences. These are divergences of the following form, where if you give me two distributions, P and Q, I compute the expected value in Q of this function of the likelihood ratio between P and Q. And there are many divergences of this type that depend on this function F. Our constraint is that this function F is convex, that at 1 it's evaluated to 0, and F is also finite for all t greater than 0. Like some of these divergences you've probably heard of, like KL divergence, you can recover it for F equals t log t. E gamma divergence, this is going to be a very important divergence for us, total variation, chi-square, and so on. And what we're going to be doing in a few minutes is that we're going to be analyzing challenges in privacy and fairness in machine learning using these divergences. So we can use these divergence metrics between distributions to measure information, to measure these changes in beliefs. Now, the second question that I ask is, how do we model information in machine learning? So in this case, what we do is that we measure data sets, or we represent and model data sets as samples from a source P of X. And when we think about a model or a training algorithm, we think about them as a channel. You can think about an algorithm, for example, a transformer model, as a channel where a sample comes in or a text comes in, and the output is a probability over the next token. Or a classifier as a channel as well, where an image comes in, and the output is a probability distribution over classes. You can also think about a training algorithm as a channel, a randomized training algorithm, a data set comes in, and the output is a distribution over weights. And this abstraction allows us to do an analysis that is independent of semantics and specific applications, and also find patterns in questions of privacy and fairness that hold across model classes and training algorithms. So these information measures and models, they're mathematical definitions, right? And historically, they've been used to quantify the limits of many engineering and computing systems. And the use of tools from information theory, of course, dates back to Claude Shannon. And what his breakthroughs allowed, among many other things, is for us to move away from ad hoc engineering, from like designing systems that transmit and communicate data that were tailored for different kinds of specific applications, and really get at the heart of the problem and distill the problem down to like a common little model that was common across these different applications. In this case, the question of data compression and data transmission could be boiled down to figure 1 in his paper, where you have an information source, a transmitter, a receiver, and so on. And by analyzing these models, you can find, he found limits of how far you can compress data and limits on how fast you can communicate or how many bits you can transmit per channel use. And obviously, there is a gap between theory and practice, right? You can't say that, oh, here's a bunch of diagram blocks in a PowerPoint slide, and just by looking at that, we can understand how to engineer a Wi-Fi router, right? But I think for me, and the power of information theory, and this is something I learned at LIDS, is that it gives us operational limits that engineers and computer scientists can aim for. And for the following decades after Shannon introduced this paper, folks have been reaching for these limits, right? Developing better coding schemes, better communication protocols, and so on. These technologies led to the widespread deployment of algorithms and devices that collect and store data at a global scale. And since the early 2000s, this data has been fueling the fast development of machine learning, which today exposes many emerging challenges. And what I do in my research, what my research group does, is that we ask, can we apply information theory to address these challenges? And this is very much in the spirit of the field. This is a picture borrowed or adapted from Cover's book, where information theory historically has found connections with many different fields that range from probability theory to statistics, communication theory, of course, physics, computer science, and economics. And what my research does is that we add another petal to this flower and ask, how can we apply information theory to understand these emerging challenges in machine learning related to questions of privacy, fairness, arbitrariness, and so on. So I want to mention one last divergence, which is this divergence between theory and practice. Like I mentioned, I'm not going to claim that just by looking at simple models, you can understand the complexity of regulating 5G networks, right? This is a much more complicated problem. And in the same way, just by looking at these mathematical models behind privacy and behind questions of fairness, that is far from perfectly capturing regulations surrounding the topic, or even the personal feeling that someone has when they're discriminated by an algorithm. But theory is only one piece of this puzzle, right? But it's an important piece. It's an important piece because by looking at theory, it helps us understand the limits of these systems, optimize and critique their design, and create algorithms and codes that massively outperform heuristics. And for me, the most precious moments in research is when we can make this divergence between theory and practice small. So that's what we're going to talk about next. Now we're going to talk a little bit about privacy and fairness. I won't have time to talk about our work on predictive multiplicity and arbitrariness. I'll leave that for next time. You can look up our papers if you're interested in that. But for the next about 40 minutes, maybe a little bit less, we're going to be talking about design and limits of privacy mechanisms and design of limits of group fairness interventions. Wait, are y'all with me? Yeah? Cool. So let's start with a little bit about design and limits of privacy mechanisms. So the flavor of privacy that we're going to be looking at today is differential privacy. Who here has heard about differential privacy? Okay, quite a few of you, great. So if you haven't, the core idea behind differential privacy is the following. You have a data set, D, and you compute a query over this data set. For example, you ask, what's the number of chefs, or the average number of chefs in this data set? And the goal of this, of differential privacy, is to measure how much your belief about the data set changes, or how much this output distribution changes, if I change only one entry of the data set. Say I change the data of the chef for an engineer here. So the goal is that a query does not significantly depend on any single individual's data. And the way you can ensure privacy in practice, and how differential privacy is ensured in practice, is by engineering this green box here, something known as a privacy mechanism. You can think about a privacy mechanism as a conditional distribution or a channel, where the input is, say, a query or maybe a data set itself, and the output is a randomized version of that query. The simplest form of ensuring privacy is by adding noise to your query. So you ask me how many chefs are in this data set, and I respond a number plus some Gaussian noise that was calibrated in order to hide the dependence in terms of individual samples. And in general, this differential privacy can be measured abstractly in terms of a divergence, right? In terms of the change in your output distribution across neighboring inputs here. So the way this is differential, one of the most popular flavors of differential privacy is known as epsilon delta differential privacy or approximate differential privacy, where we say that this green box here, this privacy mechanism, is differentially private, satisfies epsilon delta differential privacy for every epsilon greater than 0 and delta between 0 and 1, if for all neighboring data sets, the probability of any output event doesn't change by more than an additive factor of delta and a multiplicative factor of e to the epsilon. So for the rest of this talk, just to simplify a little bit the notation, we're going to substitute the condition of neighboring in terms of neighboring data sets inducing neighboring queries. So if your data sets are neighboring, your query doesn't change, the norm of your query doesn't change more by a sensitivity parameter S. And in this case, we can express differential privacy in terms of one specific F divergence known as the E gamma or hockey stick divergence, where we choose our function F to be a function that looks like a hockey stick. And in this case, you can rewrite the differential privacy in a form that is not as common, but is entirely equivalent, where we say that a privacy mechanism is differentially private if the E gamma divergence, or this hockey stick divergence, a kind of F divergence between neighboring distributions, is not greater, for a parameter e to the epsilon, is not greater than delta. And one thing that's really important is that any privacy mechanism is characterized by a range of these epsilon delta values. In practice, when you read about differential privacy disclosures, usually folks fix delta to be a small value, like 10 to the minus 6 or 10 to the minus 7, usually 1 over the size of the data set, and report the corresponding epsilon. But it's important for you to understand that any privacy mechanism, any one of these channels, is characterized by a range of these epsilon and delta values. And ideally, we want to make these very small. The smaller they are, the more private your mechanism, right? The closer to neighboring distributions are. And differential privacy is widely adopted. I think it's not an understatement to say that in many places in applied machine learning and industry, differential privacy has become the standard privacy metric. It's adopted at Google, at Meta, at Apple. In fact, it was adopted also by the US government in the 2020 decennial census. So the goal and the question that I'm going to be exploring in the rest of this part of the talk is how can we ensure privacy and how can we measure and understand the behavior of these privacy guarantees when you access data multiple times? Because when you apply a privacy mechanism, you usually don't apply it only once, right? You have your data set and you ask a query and you feed it through your privacy mechanism and you get a response, but then you're not done. Usually that data set is hosted somewhere or you're acquiring this data multiple times to train a machine learning model and you ask multiple queries, right? Either by the same or by different users. And every time this data is accessed, your privacy curve becomes looser and looser, like your privacy guarantees, they become less and less strict. So one example where data is accessed tens of thousands or hundreds of thousands of times and a privacy mechanism is applied many times is when you're doing differentially private training of machine learning models, like when you're doing differentially private stochastic gradient descent. In this case, each query for the data set is a computation of a gradient at a given parameter point. And a popular algorithm is DPSGD, where you clip your gradient and you add the Gaussian noise in order to ensure privacy. And you can assume that in this case, this privacy mechanism, in this case, clipping the gradient and adding noise, is applied tens of thousands or hundreds of thousands or maybe millions of times during training. So the idea that we had, me and my collaborators, was, well, how can we optimize privacy mechanisms for this high composition regime, right? So if we're designing these green boxes, these privacy mechanisms that add noise to the data, how should we engineer them so that we can have the best privacy for the best utility possible? And in order to answer that, we need to answer two questions. The first question is, well, how do we measure privacy loss under many compositions? How does this privacy curve behave? Right? How do these divergences increase? And the second question is how should we design privacy mechanisms that operate under many compositions? Once we can measure privacy when you're accessing data multiple times, how should you optimize the noise that you add to the data in order to achieve the best utility? So the first question that we're going to look at is this one, is how do we measure privacy loss under many compositions. So in order to understand this, we need a slightly technical, more technical definition, which is this notion of a universal privacy curve. Like at the end of the day, what we want to understand is the worst case divergence across these two distributions for the worst case pair of possible queries that someone can ask. And we want to understand how this privacy curve behaves and how it increases as you ask more and more and more and more queries. And ever since you have differential privacy, there are methods that do privacy accounting, which is essentially this process of keeping track of your privacy loss. The first methods were basic composition results. So basically what they did is that instead of considering an entire privacy curve, they considered for each use of the mechanism a specific pair of epsilon and delta values and asked, well, how can we combine these epsilon and delta values in order to get a new or an overall privacy guarantee? You can think about this as, well, each time I use a mechanism, I report a given epsilon and delta, and now if I query the data, say 100 times, how can I combine these epsilon and deltas to get a guarantee on my privacy leakage? Over the past, especially over the past 4 years, you've seen a flurry of work that tries to refine this analysis by considering the entire privacy curve. Like there are large deviations approaches, CLT-based approaches, numerical approaches, and specifically I'm going to focus on one approach we presented at ICML a few years back called the saddle point accountant. And really what made these methods work is that they focus on the concentration of one specific random variable known as the privacy loss random variable. So bear with me on this, because if you understand this part, you're going to understand really what's at the heart of differential privacy. So what is this privacy loss random variable, right? So remember that we have this green box. This green box is our channel. It's our privacy mechanism. We're going to ask a query on the data, and then we're going to randomize that query in order to output a randomized value in order to ensure privacy. And we measure privacy in terms of neighboring queries, right? So we can define this random variable known as the privacy loss random variable, which is nothing more than the log likelihood ratio between the output distributions if the input were x or x prime. So it's a log likelihood ratio that you would see when you're testing between these two distributions. And here we're assuming that y is distributed according to p of y given x equals little x. So the mean of this random variable is, anyone? KL divergence, great. That's how you know you're at MIT. So the mean of this random variable is KL divergence, right? It's the KL divergence between these two neighboring distributions. So remember this, because this will be important for us later. Why? Because eventually we're going to be accessing the data multiple times, and the random variable will concentrate to its mean. And we can write this privacy curve in terms of the privacy loss random variable. It's a pretty straightforward exercise in algebra just to rewrite this E gamma divergence that captures your epsilon delta guarantees in terms of this privacy loss random variable. We still have this annoying subterm here to get the exact delta, where you have to look at the supremum across all neighboring distributions. You can get over that by looking at something known as a tight privacy loss random variable. Basically, you create a pair of random variables whose E gamma divergence, whose privacy curve dominates those for any pair of neighboring distributions. So we can, in many cases, create a tight privacy loss random variable. Often it's just the distribution that you get for the privacy loss random variable for the worst case inputs. And in this case, you can write your privacy curve as a function of this privacy loss random variable. And since this is a log likelihood ratio, when you're querying the data multiple times and you're considering this worst case PORV, your privacy guarantee becomes a sum of these privacy loss random variables, right? So the problem of privacy accounting boils down to quantifying the sum of these usually IID privacy loss random variables. And over the past few years, you've seen several papers that try to do exactly that. So one natural approach is for you to approximate this sum using the central limit theorem. In this case, you approximate the sum of the privacy loss random variable by a Gaussian. Naturally, another approach is that you look at the cumulant generating function of this privacy loss random variable. This is a large deviations approach. This is what's at the heart of something called Rayleigh differential privacy and the moments accountant. In this case, you apply a Chernoff bound for the using the cumulant generating function of your privacy loss random variable, which is essentially Rényi divergence for neighboring distributions. But the challenge of these approaches is that they're nice because they give us an analytical form of your privacy loss. And remember, ultimately, where we're going with this is that we want to optimize our noise distributions. But they can be not very tight. Like RDP can overestimate your privacy loss, and the Gaussian differential privacy can underestimate your privacy loss. So if you have a bunch of distributions, right, and you're adding them up, and you want to compute the density of this sum, you can convolve the individual densities. And what's a fast algorithm for computing convolution? The FFT, yeah. And this is another set of approaches known as the FFT approaches that does exactly that, that you numerically compute the convolution via the FFT. So here you have a set of accounting procedures, one that gives you nice analytical forms that later we can optimize, but has relatively low precision. And the other one that's purely numerical, so it's something that's purely computational, but gives you incredibly precise approximations of your privacy loss random variable. So we proposed an alternative approach a couple of years back at ICML called the saddle point accountant, which is nice because it has an analytical form and it has high precision. And it's just one key trick that we use. And one key idea is that instead of looking at the concentration of the privacy loss random variable, we look at an exponential tilting of the privacy loss random variable. So what do I mean by exponential tilting? That we create a new random variable, L tilde, whose distribution is the tilted distribution of your random variable L. And here K is your cumulant generating function. So for example, if you have a continuous random variable, if you have a density for your privacy loss random variable, the distribution of your tilted distribution is just your original density times this term, where again, K is your cumulant generating function. And tilting distributions are very nice. This is a common trick used in large deviations theory because the first property that they satisfy is that if your underlying distributions are independent, the tilted distributions are also independent, that the tilting of the sum is the sum of the tilts, and we can also measure the value of certain functions of this random variable in terms of its tilted distribution. And it's particularly this third property that we use here, because what we do is that we re-express your privacy curve in terms of the tilted distribution of your privacy loss random variable. And when you look at this, at your resulting delta guarantee for a given epsilon in differential privacy for the tilted version, you can, in the large composition regime, you're gonna have the sum of multiple random variables, and you can approximate it using the central limit theorem, but now applying the central limit theorem to your tilted distribution. And that's at the heart of the saddle point accounting. When you look at this formula here, you can actually apply Parseval and write it in the Fourier domain. So you can write it in terms of the moment generating function of your tilted distribution, or the characteristic function of your tilted distribution. And then you can write your privacy guarantees in terms of an integral, where t here is exactly the tilting parameter that you choose. So in a sense, the tilting parameter determines the real intercept of this line integral that you're solving. And again, k here is your cumulant generating function. So if you look at this exponent here, and it's imaginary, and it's a complex exponent. And if you plot it in the complex plane, this function has a saddle point here. And this saddle point is where we choose our integration point. And that's something that's very common in mathematical physics. It's known as Laplace's integration method, and we apply it here. And once you do this, you get a very precise approximation of your delta epsilon curve. You can derive bounds for this as well, where the point that we choose our tilting is exactly the solution, the unique solution of that saddle point. If you're familiar with Rényi differential privacy, or the moments accountant that was proposed a few years ago, you can think about this as a correction of the moments accountant, where you add this additional denominator here in order to, and these additional terms when you're computing your integral. And the result is that this gives us approximations that are very, very accurate, including in the tails, for your privacy loss. So what you see here are the black line are upper and lower bounds given by the saddle point accountant. The blue line is what you get by computing the FFT. Eventually, it stalls out because of numerical precision. Of course, you can always improve your FFT to handle larger precision, but this is what we use out of the box in Python. And you can see that our approximation is very precise and more precise than the moments accountant, for example. So, because in part we're information theorists as well, a natural question to ask is, well, how does privacy behave when you're in the regime where you have an extremely large number of compositions, right? If you're accessing data hundreds of thousands or millions of times, right? This very asymptotic regime where you're accessing data multiple times. And you can ask, well, can we derive something that looks like a capacity result here? So if you were to fix a given delta, at what, so usually in practice, as I mentioned, delta is fixed to a value of 10 to the minus 6 or 10 to the minus 7, 1 over the size of your data set. You can ask, well, how does your epsilon grow with the number of composition k? And can we characterize this linear growth rate of your epsilon guarantee and epsilon delta differential privacy? So the goal is that for a fixed delta, can we characterize the growth rate of this privacy curve? And specifically, we want to characterize this growth rate across a range of possible mechanisms, right? So the constraint that we ask is what is the smallest privacy per composition, epsilon here, given a distortion constraint, right? So over all possible mechanisms where the distortion at the output is bounded, for example, the MSC is bounded, what is the smallest possible growth rate that we can achieve in terms of epsilon per composition? So, and we define the set of mechanisms that satisfies this distortion constraint by cal R here. This is the set of mechanisms that satisfies our target distortion. And we can ask, again, the question that we're asking is what is the smallest privacy per composition given across all mechanisms that satisfy this distortion constraint? And we define this quantity as privacy capacity. So this epsilon star for a given alpha norm here and for a given cost constraint C in your distortion, our goal is to characterize the infimum across all achievable privacy growth rates in this problem. This is something that we presented at ISIT last year, and we say that growth rate epsilon is achievable if we can design or there exists a mechanism P of y given x such that this growth rate in epsilon is smaller than epsilon for some delta that doesn't decrease too quickly. So there's an analogy for privacy capacity in terms of rate distortion theory, where here C plays a role of distortion, rate distortion theory. You can think about K as your block length, and delta here almost as your decoding error probability. So it turns out that privacy capacity, this growth rate of your epsilon as you query data multiple times, is related to another quantity, which is the min-max scale divergence. So you can ask, across all mechanisms in this set that satisfy a given distortion constraint, what is the worst case scale divergence across all neighboring distributions? So you can think, for example, that what across all distributions that satisfy a given constraint, for example, two Gaussians, what is the worst case scale across all possible shifts? And it turns out that in this limit of many, many accesses to the data, your privacy rate, your privacy capacity, the linear growth rate of epsilon is equivalent to your minimax scale divergence rate. So in a sense, in this case, your privacy guarantee single letterizes, and the role of like, if you would have like mutual information in rate distortion theory, here you have the min-max scale divergence across neighboring distributions. But not only that, we can show that for, if you're, for the cost constraint that we're considering, these norm cost constraints, we have that additive, continuous, and spherically symmetric mechanisms can achieve privacy capacity. So what this means is that even though we're optimizing over an abstract set of channels, it's sufficient to design an additive noise to your query in order to achieve this capacity. That there, in other words, there exist additive noise distributions that achieve privacy capacity. This is interesting for us because now we can try to optimize the PDF of this noise in order to achieve favorable performance in this large composition regime? And this is the second question that we ask. So how should we design privacy mechanisms that operate under many compositions? So just to recap where we are. So again, the goal is to design privacy mechanisms that minimize privacy loss and maximize utility. Ideally, we would want to do this by computing the privacy curve exactly, but that's very hard. We can only compute it using things like the FFT. Ongoing work is actually optimizing the saddle point accountant method. It's kind of complicated because you have to back propagate through an OD, so it's not super simple to do that. What I'm going to show you today are results that we already published where we optimize for privacy capacity. So we optimize for this like limit of the growth rate of epsilon. In this case, you have this optimization problem where you're minimizing KL divergence subject to a cost constraint. As I mentioned before, you can show that it's sufficient to consider additive mechanisms. So the optimal thing to do is to optimize the PDF or PMF in the discrete case of the noise that you're adding to your data. And that's exactly what we do. Like we quantize this PDF and solve it numerically. So if you squint at this problem, you can probably see that it's a convex optimization problem. So we can just kind of brute force numerically solve it. So you can quantize this PDF, right? You can just quantize it in multiple buckets in the one-dimensional case and solve this very complicated, this optimization problem that looks pretty complicated, but it's still convex. So you can solve it using standard interior point methods. This is the convergence of your optimization problem. You can see that it converges to a very kind of crazily shaped noise distribution. We call this the cactus distribution because of like the other authors of this paper, they're from ASU. So they think a lot about cactus, I guess, and it has this nice spiky distribution. And you can do this for multiple dimensions as well. This is the PDF of the radius of the noise in 10 dimensions. And the optimized noise distributions, they do not look like Gaussian. They look like something different. And here we're looking at 10 dimensions, delta equals 10 to the minus 8, and a MSC distortion constraint. And you can see that it achieves a more favorable privacy decay for the same distortion level. And as I mentioned, this is how it looks in one dimension. This is the PDF of the noise in one dimension. It looks like a cactus. These noises are optimized to be better in terms of KL divergence, right? So you can compare the maximal KL divergence across worst case neighboring inputs for our optimized noise distributions and Gaussian. And if you look at this curve, so here on the x-axis you have the MSC, right, the standard deviation of the noise. On the y-axis, you have your maximal KL divergence. And here we're considering a sensitivity of 1, a shift of 1. But what's interesting is that, not surprisingly, the optimized noise distribution is better. It has a lower maximal KL than the Gaussian distribution. But it seems that there are certain regimes where Gaussian is optimal, right? And so when we first saw this graph, it got us thinking, like, what's happening here? Like, we went through all this trouble of like understanding how privacy behaves in the large composition regime. We quantized, we found a setting where like additive mechanisms are optimal. We can quantize the PDF and formulate this giant convex optimization problem. We get a noise distribution out of it. But it seems that in certain regimes, it's hard to beat Gaussian. It seems like Gaussian is pretty good. So what's happening? And it turns out that there's something really interesting happening in this regime, that in the small sensitivity, high noise regime, optimizing differential privacy mechanisms is equivalent to finding eigenfunctions of the Schrodinger operator. So surprise, physics. And so let's go through this. So this follows from a property of KL divergence. So if you look at KL divergence, so if you look at the optimization problem that we're looking at, here T of A is the shift operator. And we're looking at the PDF that minimizes the worst case KL divergence across all possible shifts of a distribution with itself. This is the simplest form in one dimension, subject to a cost constraint. We're assuming in the simple one-dimensional case that the cost constraint is something of this form. Like you can think about alpha equals 2 and we're minimizing MSC. But what happens when you make your sensitivity very, very small, when you make the shift very, very small, you can approximate a KL divergence up to the first order term of its Taylor series expansion on the shift in terms of Fisher information. So for small shifts, scale divergence behaves locally like Fisher information, wherein Fisher information is defined here. So in this case, if your shift is very, very, very small, or equivalently the noise that you add is very, very large, you can approximate this optimization problem by minimizing the Fisher information subject to a cost constraint. And you can show that this optimization also has a unique optimizing distribution. Now, the thing that's surprising here is that, again, in this small sensitivity regime or equivalently large noise regime that you're adding to the data, the Fisher minimization problem, it boils down to that solving this optimization is equivalent to finding eigenfunctions of the Schrodinger operator. And what I mean by that is the following operator given here. So if you have a measurable function v, the Schrodinger operator h of v over this, the space of squared integrable functions with the potential function v is given by this operator here. You take a function y and you compute its second derivative and add it, change the sign and add it to v times y. And we say that a function is an eigenfunction for this operator if there exists an e such that when you apply the Schrodinger operator to the function, you get the function back. So it turns out that you can relate the optimization problem to finding eigenfunctions of this Schrodinger operator, where you adjust this potential function to be related to your cost function here. And theta, you can think about this almost like a Lagrange multiplier that defines what value of the cost that you're going to achieve. And the theorem here, and this is a theorem that is not ours, it has been observed in other work as well, that in this case, we can define a new noise mechanism that we call the Schrodinger mechanism, where we add noise to your query, where the noise is taken from a PDF whose distribution is equivalent to the square of the eigenfunction that achieves the unique smallest eigenvalue of this Schrodinger operator. And you can show that in this case, the square of this eigenfunction is exactly the PDF of the noise that you would add. So the takeaway that I want you to get from here is that KL optimal privacy mechanisms in the small sensitivity regime are given by eigenfunctions of the Schrodinger operator. So when you choose your cost function to be quadratic cost, then and find the corresponding eigenfunction, this is a known result in mathematical physics. The eigenfunction is exactly the Gaussian. So this explains why Gaussian is optimal, right? Why we observed this favorable performance of Gaussians in this small sensitivity or large noise regime. What's interesting is to explore other kinds of constraints. So you can ask, what happens if I add an L1 constraint here? So in this case, one might expect that you're going to get something that looks like Laplace noise, which is a very popular mechanism in differential privacy, but in fact you don't. The optimal noise distribution is something known as an Airy distribution that's given in terms of these Airy functions. We haven't seen this in differential privacy, and we call this the Airy mechanism. Compared to the Laplace noise, to the standard Laplace mechanism, these distributions are actually quite different. Not only in terms of their shape, but also in terms of their tail. So if you look at a Laplace tail, like it falls as e to the minus x. If you were to look at a Gaussian tail, it's e to the minus x squared. And for the Airy mechanism, you get something in between. So these are the two questions that we were asking, and we've been studying for a few years now. So the first one is, how do we measure privacy loss under many compositions, and how should we design privacy mechanisms that operate under many compositions? And I think by now we have a really good handle of how these epsilon delta privacy guarantees behave in the limit of large compositions. The question of how to design optimal mechanisms is still ongoing work. What we've been observing in our experiments is that many machine learning settings of interest is this kind of small sensitivity regime. So effectively your data is very large, or you have many parameters, and in that case Gaussian performs really well. So it might turn out that what people have been doing all along of adding Gaussian noise to data is actually optimal, or really close to optimal. But at least now we can show that beyond just a heuristic. So in the 10 minutes that I have left, I just want to switch gears a little bit and just give some high-level overview of some of the work that we've been doing on fairness. Particularly if anyone is interested in collaborating with folks down Mass Ave and across the river. So just for the last 10 minutes, I'm just going to highlight some of our contributions here. So the challenge we've been asking for a while is the challenge of group fairness, which is if you give me a classifier and a data set, right, I train this classifier, and I want to ensure that this classifier is not only accurate on average, but across different population groups, there's no significant difference in performance. And by difference in performance here, I mean, for example, differences in accuracy or false positive rates or false negative rates. And what I mean by population groups, I might address this again towards the end, but what I mean by that are groups, for example, this has been since taken down, I believe, by the White House, but to avoid discrimination against groups determined, for example, by race, color, ethnicity, sex, and so on. So there are many methods that, and many metrics to measure this disparity in performance in so-called group fairness. And usually they follow the following recipe, at least for binary classification tasks, where you have an input example, and you have a classifier output, and you have a binary group attribute. And then you can, denoted by S, for example, two groups here. And if you're doing binary classification, you can build group fairness metrics by building this confusion matrix between both groups and comparing their entries. So for example, if you train a classifier and you want the average number of ones, the average number of inputs marked as 1 across both groups, you're trying to ensure something known as statistical parity. You might want to equalize false positive and true positive rates. That's known as equalized odds. But you can already see that there's combinatorially many different ways of defining fairness metrics in terms of how your model errs. When your classifier outputs a risk score or a distribution over classes, so for example, when you think about your classifier as a conditional distribution that outputs a distribution over a certain set of classes, you can also extend these these fairness definitions, statistical parity, equalized odds, and so on, in terms of this output distribution here. So something that will be important for us in just a few slides is that several score-based group fairness metrics can be written as linear constraints on the classifier. So this is an important insight because it will allow us to formulate optimization problems where we add these group fairness constraints as linear constraints and try to minimize the change in the output of the classifier. But over the past 10 years, there's been just myriad fairness interventions. They can be broadly divided into pre-processing and processing and post-processing methods, where you change the data before you train, in-processing methods, where you change the classifier while training, and post-processing methods, where you correct the outputs of a classifier. And usually these interventions are compared in terms of these fairness utility trade-offs. So here on the y-axis, you have accuracy. On the x-axis, you have some kind of fairness metric. And you compare what accuracy on average does your model preserve while closing some kind of disparity gap. And in fact, there was a study recently that showed that this is already from last year, so this number probably increased, that there were 341 publications with over 400 methods proposing different fairness interventions. So our goal was well, can we design a better fairness intervention? And specifically, how can we show that maybe we're approaching some kind of Pareto frontier of the best that you can do? So our goal was to design a fairness intervention that worked for large data sets, multiple classes, and multiple potentially intersectional groups for ensuring performance. And there are many fairness interventions out there, but most of them have certain limitations. They were benchmarked on overused data sets like Ableton and Compass that were pretty small. They only consider either binary classification or only consider disparities in performance in two groups. So in Europe, a couple of years back, we proposed a new fairness intervention called fair projection that overcomes these limitations. We benchmark it on a data set with over 1 million samples. It can be applied to any classifier without retraining. It's a post-processing method. So the complexity is the same if you're training a neural network or if you're training a logistic regression. And it can be used for any finite number of classes and protected groups. And fair projection is actually based on an optimization formulation known as information projection that you might be familiar from your information theory class. Where the vanilla information projection you have a distribution P, and you want to project onto a convex set of distributions Cal of C that are determined by a finite set of moment constraints. So the idea is that if you have a reference distribution P, you want to find a new distribution Q in the set that minimizes the quote-unquote distance, often formulated in terms of KL divergence, subject to being in this class. And this finds many applications in large deviation theory, universal source coding, compression, and beyond. You can actually generalize this projection operation in terms of a F divergence. So you can ask, what is the closest distribution in terms of a given F divergence? And you can further this was done by Cheeser in the 70s, and you can actually further generalize this, and instead of projecting a single distribution, you project a conditional distribution, a channel, right? And you can ask, well, what is the channel within a set of channels that satisfies a convex set of moment constraints that minimizes this conditional F divergence? We presented this at ISIT already now a few years back. It's not a direct extension of information projection. You have to take a little bit of care to show that the solution to this optimization is well defined. And model projection is very useful for ensuring fairness, because in this case, as I mentioned earlier in the talk, you can think about your conditional distribution as your model, right, as your classifier. So you can think about a classifier as a channel where a sample comes in and a distribution over classes comes out, right? And as I mentioned earlier, the set of group fairness, several group fairness constraints can be written as linear constraints on this classifier. So you can formulate the problem of minimizing the changes of the output of a classifier, or finding a new classifier that minimizes the average change of the base classifier, but also satisfying your fairness constraint as an F divergence minimization problem that looks like model projection. And you can prove that the optimal output, the optimal classifier that you get is actually a tilting, just like we saw earlier, but now an F divergence dependent tilting of your original classifier, where these dual parameters, these parameters of the tilting depend on your F divergence of choice and on your fairness constraints. And this is the basis of an algorithm that we proposed that was an oral at NeurIPS a couple of years ago, called fair projection, which is a model agnostic post-processing approach that can be applied to any base classifiers. So if you buy this model projection framework, this is that post-processing is the best thing to do. And we tested this as well. You can implement this. This algorithm is highly parallelizable. You can solve it using ADMM. This is the algorithm for fair projection. I'm not going to go into details, but the important thing is that you can parallelize it and run it on a GPU using standard proximal ADMM-like algorithms. And we benchmarked it on several data sets that are of a nation-state scale with this is a data set from the Brazilian university entrance exam with over 1 million samples. And this is restricted to binary classification because most competing methods at the time were only restricted to binary classification tasks. And you can see here the dark red line, which is fair projection, is competitive with the state of the art. In this case, our base model is a random forest classifier. The most competitive method to ours was the reductions approach, but our method ran 100 times faster exactly because we can parallelize it on GPU. And since then, we've tested it on other methods also for correcting neural networks and things like that. So the last thing I'm going to mention is that if you look at this plot, it seems like there's some diminishing returns here, right? It seems like, oh, we're optimizing this fairness correction process, but it seems like we're not getting a lot out of it. So there's a question, are we close to this best fairness accuracy frontier? For example, is there something like a converse bound that we could show that proves that maybe we're already very close to the best that we can do? And this is something we presented at NeurIPS 2023, that in fact, we can, for certain semi-synthetic experiments, derive this converse bound. It's based on a result by Blackwell's comparison of experiments. And for popular data sets, you can show that we are actually very close to optimal. So yeah, I'm going to wrap up here. So if you found this interesting and you're looking for folks to collaborate around the river, we have Also other ongoing work and that range from like pure kind of Shannon theory kind of things on measuring information from moments to things that are more coding theoretic flavored, like approximate coding computing and private vector database retrieval, work on like trying to understand the generalization properties of learning algorithms based on these information theoretic quantities. And to wrap up, just going back to the divergence between theory and practice. So information theory can help guide the design of trustworthy or more trustworthy machine learning algorithms through formulations that are imperfect, right? Specifically when you talk about like regulation of privacy and I don't know, ethical aspects of fairness, but they are good because they're formal. They can be analyzed, critiqued, and tested. Another thing we've been doing in my group is also trying to bring these things in practice, both with outreach programs in Latin America, to collaborations with like the OpenDP project at Harvard, which is a big project for developing open differential privacy software. We actually wrote a policy brief that was published at the G20 meeting in Brazil about arbitrariness and fairness in machine learning and so on. We have a big research group. My research group is now about 12 people, all thinking about things that are very close to the LIDS student heart, like learning data optimization, information theory, and so on. And I would be happy to answer any questions. Thanks.